Hello, this video explains the Steinhardt parameters that are implemented in Plumed and which can be used to probe whether or not a structure is solid-like or liquid-like. This tutorial gives a bird-eyes view of the theory of these parameters and is far from exhaustive. If you are interested in using these parameters, you should also read some of the many articles in which these quantities have been used to study nucleation or crystallization. Let's start by thinking about the difference in the arrangements of atoms in solids and liquids. The image on the left shows the arrangement of atoms in a solid, whilst the image on the right shows the arrangement of atoms in a liquid. Let's now consider the coordination number of the blue atom in these two systems. As you can see, in the solid, the first coordination sphere contains 4 atoms. In the liquid, the first coordination sphere also contains 4 atoms. Thus, the coordination numbers in the solid and liquid are the same. What is different is the arrangement of the atoms. In the solid, because of the ordered structure overall, the arrangement of atoms in the first coordination sphere is very ordered. By contrast, in the liquid, because there is no long-range order, the arrangement of atoms in the first coordination sphere can be quite disordered. Thus, the basis of many collective variables that distinguish between the solid and the liquid states is recognizing whether or not the first coordination sphere around the atoms is ordered or disordered. The Steinhardt parameters are variables of this type, and these have commonly been used to distinguish between the solid and liquid states. This is the main equation that is used within Plumed to calculate these quantities. Much like the coordination number, the Steinhardt parameter is a symmetry function. There is thus one Steinhardt parameter for each of the atoms in the system, and it is calculated by considering the vectors connecting this central atom to all the remaining atoms in the solid or liquid. Let's look at the various parts of this expression term by term. Sigma Rij is a switching function that acts on the distance between atom I, the central atom, and atom J. This term ensures that we only consider the ordering of those atoms in the first coordination sphere of atom I. Atoms in higher coordination spheres are essentially ignored. Furthermore, because sigma appears in both the numerator and the denominator of this expression, the final quantity is a weighted average of these YLM terms. Each of these YLM terms is a function of one of the Rij vectors. To be clear, these are the vectors connecting the central atom, the blue atom in the figure, to each of the remaining atoms in the system. YLM is a special function known as a spherical harmonic, and it can look something like this. As this figure shows, the spherical harmonic function is defined on the surface of a sphere and is rather complicated. The value of the function is actually complex, which is a detail that I'm glossing over here, but is something that you should definitely look into in more detail. For the time being, we will proceed by recognizing that when vectors point from the center of the sphere to the red parts on the surface of this sphere, YLM equals 1. By contrast, when the function points towards the blue parts on the surface of the sphere, YLM equals -1. If you examine the pattern of red patches on the surface of this sphere, you will see that they are arranged in a regular pattern. A similar thing holds for the blue patches. They are all about equidistant apart on the surface of the sphere. The consequence of this is that if the arrangement of atoms around the center is ordered, then the bonds between the central atom and its first coordination sphere, the Rij vectors, will all point towards patches of the same color. Consequently, every term in the sum will contribute either +1 or -1 to the total. By contrast, if the pattern is disordered, as it would be in a liquid, there will be bonds pointing towards the red patches and bonds pointing towards the blue patches. There will thus be terms that contribute +1 in the final sum and terms that contribute -1, and these two distinct types of term will essentially cancel each other out. There are a number of different spherical harmonic functions which all have different patterns for the red and blue patches. The particular function you will need for your problem will depend on the system that you are studying. You control what function you use by adjusting the L value, and this L value can take a value between 0 and infinity, any integer value. We will come to M in a moment. In applications looking at solid-liquid transition, L equals 4 and L equals 6 are common choices. This slide shows pictures of the first 25 spherical harmonics. Each row shows the spherical harmonics that have a particular value for L. So the first row shows those spherical harmonics that have L equals 0, the second row those that have L equals 1, the third those with L equals 2, and so on. You will notice that for L greater than 0, there are multiple spherical harmonics with a particular L value. In fact, in general, the number of spherical harmonics with a given value for L is equal to 2L plus 1. This is why, when specifying the particular spherical harmonic function of interest, we need two values. The M value tells us which of the 2L plus 1 spherical harmonics in particular we are interested in looking at, and in general, M goes from -L to +L. When we were looking at the previous slide, I suggested that commonly used L values are 4 or 6. These are the Steinhardt parameters that are most commonly used to examine the solid-liquid transition. I said nothing about which M value to choose. The reason for this is that when we calculate the Q6 Steinhardt parameter, for instance, we consider all 13 of the possible values for M simultaneously. That is to say, we calculate 13 quantities using the equation from the previous slide, this equation. The reason we do this is best explained by considering the three functions with L equals 1. If we look at the middle of these three functions, for the magnitude of QLM will be large when the atoms are arranged like this, or like this. It will be small if they are arranged like this. This is good as these are markedly different configurations. One is linear, whilst the other has C2V symmetry. Suppose now that I rotate my frame of reference by 90 degrees. Now all three configurations have small QLM values because there are no bond vectors pointing to red or blue patches. In these non-red or non-blue regions, the value of YLM is 0. The configurations are to all intents and purposes the same, however. It is simply that our frame of reference has changed. Look now at the first of the spherical harmonics. When we use this spherical harmonic in the formula, we once again find that the two configurations on the left have large magnitudes for QLM, while the configuration on the right has a small QLM magnitude. The point of this exercise is to explain that while the L value controls the pattern of blue and red patches on the surface of the sphere, the M parameter controls the orientation of the pattern. So for L equals 1, we have a pattern containing a blue patch on a red patch on either end of a line. There are three orthogonal ways we can arrange this pattern. The blue patch can be above the red patch, the blue patch can be to the left of the red patch, or the blue patch can be behind the red patch. As you can see from the figure, the three L equals 1 spherical harmonics reflect these three distinct and orthogonal arrangements of the pattern. This is why we calculate all the spherical harmonics values with a given value for L when we calculate this order parameter. This ensures that we have descriptors that tell us whether or not the pattern of bonds is ordered, and also that we have descriptors that don't particularly care about the orientation of this ordered pattern. All possible orientations for the pattern for a given L value are a linear combination of the 2L plus 1 spherical harmonics with that particular L value. There is an important point to note here. Let's apply the procedure described thus far to the blue atom here, say. We first identify the first coordination sphere using a switching function. We then use the vectors connecting the central atom to each of the first atoms in the atoms in the first coordination sphere to calculate all the spherical harmonic values for the L value of interest. What we extract using this procedure is an ordered set of numbers, a 2L plus 1 dimensional vector, a number with both magnitude and direction. Not direction in the two-dimensional plane as illustrated here, but a direction in some 2L plus 1 dimensional space. This is what is calculated by the Plumed command shown here. There is a problem here though. Most of the things that you know and love in Plumed work with scalar quantities. We must therefore find some way of converting these vectors into scalars. The most obvious way of doing this is to take the norm, i.e. to calculate the magnitude of the vector. This is done using the equation shown. The final step before using these things is to recognize that the Steinhardt parameters are implemented in Plumed as multi-Colvars. We can thus use the command shown to calculate all the Steinhardt parameters for all the atoms in the system. We could then take the magnitude of all these vectors and do all the normal things that can be done with multi-Colvars, namely more than, less than, min, mean, and so on. We can also use these vector quantities in multi-Colvar functions and calculate more complex collective variables, but this will be the subject of a separate video. Thank you for your attention.